Hi all, welcome back to chapter 10. We are focused on the molecular geometry portion of this chapter, and we're not going to go into hybridization of atomic orbitals. So let's finish up chapter 10 here. And so in this topic in chapter 10, we'll be predicting bond angles in molecules with one central atom and no octet rule exceptions. So previously in chapter 10, part 1, we focused on all bonding pairs essentially from a central atom. Here, however, we're going to start to look at if one of those groups is not just bonds. These are all 4 CH bonds from the central carbon. So hydrogen, 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 and hydrogen. These are all bonds coming from the central atom. And so if there are 4 regions of electron density, we know that is a tetrahedral. That is a tetrahedral arrangement of electron groups. So 4 groups around the central atom. For tetrahedral, the bond angle is 109.5. Next, now I mentioned if we start to replace one of these groups with a lone pair or even 2 lone pairs of electrons, lone pairs of electrons will repel more. They will take up more space. So seen here, that's a lone pair of electrons taking up a lot more space than just a bond does from the central atom. So in this case, we have 3 bonds from the central nitrogen and then a lone pair. While this is still 4 groups around the central atom, now one of those groups is a lone pair of electrons. Then in this structure for water, we have 2 bonds from the central atom, but then 2 lone pairs off the central atom, still for 4 groups off the central atom in total. So by group, we know from last time in chapter 10, part 1, groups are considered 1 lone pair of electrons, a single chemical bond, or even a double and triple bond. Those all just count as 1 group of electrons. And specifically, these are the groups of valence electrons because valence electrons are what are responsible for chemical bonding. So those valence electrons in the outer shell, those are responsible for chemical bonding. Groups of valence electrons or groups of electrons we think of within these 3D structures and Lewis dot structures, those groups can be a lone pair, single bond, double, or triple bond. So here are the groups. We still have 4 groups in total. 2 of those groups are lone pairs of electrons off of oxygen, and the other 2 are bonds to hydrogen atoms. So 2 electrons here in a bond, 2 electrons here in a bond, 2 electrons here just as a lone pair, 2 electrons here just as a lone pair. Lone pairs of electrons take up more 3D space. So lone pairs of electrons will repel one another the most. They take up more space. Then next, as far as repulsion, a lone pair and then a bonding pair will then repel each other next. As far as decreasing order of repulsion, the least amount of repulsion are the bonding pair and bonding pair of electrons, meaning that if 2 atoms are in bonds, they can be a little bit closer to one another than 2 lone pairs of electrons that will repel each other the most and again take up the most physical 3D space. So lone pairs of electrons again take up the most 3D space. Why this matters here is because this impacts the bond angle. When there are no lone pairs of electrons and only bonds for tetrahedral, this is 109.5 degrees. When we add a lone pair of electrons and it replaces one of these bonds, that lone pair of electrons, again, will take up more space. It's going to push these 3 bonded groups closer to one another to compress this bond angle here. So now this is a little bit less than 109.5, it's 107.3 degrees. Then within tetrahedral arrangement of electron groups, we add in 2 lone pairs of electrons. Those lone pairs of electrons will repel each other a lot and take up a lot of 3D space. That means this bond angle is even further compressed. So these atoms from the bond can be closer to one another compared to these lone pairs of electrons. So again, this bond angle only about 104.5. Coming back to chapter 10, part 1 to show you this reminder, the arrangement of electron groups. When we're talking about the arrangement of electron groups, we're talking about all the groups. Lone pairs, single bonds, double bonds, triple bonds, all groups are considered under the arrangement of electrons. So if we're thinking about just the arrangement of electrons, we will think about all the groups. When we're thinking about the molecular geometry or the specific shape, then we start to consider, are those groups lone pairs? Are they single bonds? Are they double bonds? Are they triple bonds? So bonds are now differentiated from lone pairs when we're starting to talk about the actual 3D shape and molecular geometry is the wording here. So let's apply these 2 different ones to the case we've been looking at so far. If we're just talking about the arrangement of electron groups for all 3 of these examples, we have 4 groups, 1, 2, 3, 4. Yes, all bonds here, still 1, 2, 3, 4, 3 bonds and a lone pair. 1, 2, 3, 4, 2 bonds and 2 lone pairs. So just saying arrangement of electron groups, we have 4 groups off the central atom. We're not differentiating yet a lone pair versus a bond. So 4 groups, that is tetrahedral arrangement of electron groups. It doesn't matter that some of them are lone pairs and some of them are single bonds. This is different, though, we know, from talking about the actual molecular geometry or the shape. When we start to now talk about the actual molecular geometry or the shape, these are different. Just talking about the arrangement of electron groups, these are all tetrahedral, they're all the same. But again, when we start to talk about molecular geometry or the shape, this is a different shape than this, because this has 1 lone pair and 3 bonds, 2 lone pairs and 2 bonds, versus all 4 just bonds. And so we'll come back to this slide number 7 here when we have 4 electron groups. The arrangement of electron groups or pairs is all tetrahedral. But when we start to talk about the molecular geometry, 4 bonds, no lone pairs, we still call that shape or molecular geometry as tetrahedral. However, now under the category still of tetrahedral arrangement of electron pairs, when we have 3 bonds and 1 lone pair of electrons now we call this trigonal pyramidal. Then still within the category of 4 electron groups and still tetrahedral arrangement of electron pairs, when we have 2 bonds now and 2 lone pairs, we call that molecular geometry or shape as bent. So we'll come back to this slide. I wanted to give you a preview of that. So electron pairs, the arrangement, that's for the total number of groups, regardless if they're bonds or lone pairs. The molecular geometry or shape, however, that is different based on how many lone pairs versus bonds there are. And so again, because lone pairs of electrons take up more 3D space, they repel one another more, we will have different bond angles. All bonds and no lone pairs for tetrahedral arrangement of electron groups is a bond angle of 109.5 here. Still under tetrahedral arrangement of electron groups, but now we have one lone pair and then 3 bonds. That bond angle is a little less than 109.5, so it's 107.3 degrees. Then still 4 total groups, but 2 of these groups are lone pairs, 2 of these groups are bonds. That bond angle now is even a little bit less than 107.3. This bond angle here is about 104.5. So I wanted to start with this example with tetrahedral. This first table we're going to look at, though, is just looking at 3 electron groups. For 2 electron groups, that is always linear. So this is chapter 10, part 1, slide 3. 2 electron groups, that is always linear. We won't see a case where we'll have 1 bond and 1 lone pair. So again, 2 groups around the central atom, that is always linear. That's why we're jumping in here in chapter 10, part 2, with now 3 electron groups. So when there's 3 electron groups, this is trigonal planar arrangement of electron pairs. 3 bonds, no lone pairs, that molecular geometry then is still trigonal planar. But when we have 1 lone pair amongst those 3 groups and 2 bonds, this is still trigonal planar arrangement of electron pairs. But now this is bent molecular geometry. So that lone pair occupies more space. It's going to push this bond angle a little bit closer to one another. So these bonds can be a little bit closer. So when we do have a lone pair here, this is more of a bent molecular geometry. So still 3 groups in total, but bent versus trigonal planar. Now we're back here to 4 electron groups. So the arrangement of electron pairs, when there are 4 groups, no matter if they're lone pairs or bonds, those are both tetrahedral. So we'll get to the slide we were at just a moment ago. So slide 7 is here. Here we're just looking at 4 bonds, no lone pairs. Molecular geometry, still tetrahedral. 4 groups in total, 3 are bonds and 1 is a lone pair. That's what we saw for ammonia or NH3. So still tetrahedral arrangement of electron pairs, but now the molecular geometry is considered trigonal pyramidal. So this lone pair here occupies more space than these bonds, so it'll push those bonds closer to one another. So this is now trigonal pyramidal because we have a lone pair here rather than all 4 bonds. So now we're back to slide 7, and so we looked at now if there are 2 bonds and 2 lone pairs, we still call that tetrahedral arrangement of electron pairs. But the molecular geometry name or the shape when there are 2 bonds and 2 lone pairs, this is what we call bent. And so a classic molecule that you'll know now after Gen Chem 1 is water. Water is H2O. To draw the Lewis dot structure that works best for water will look like this. This is still 4 groups around the central oxygen, so 2 bonds, 2 lone pairs. That's 4 groups. Water is tetrahedral arrangement of electron pairs. But the molecular geometry or the shape of water, it's considered bent. So 2 bonds, 2 lone pairs, it's going to compress these bonds here closer to one another because those 2 lone pairs take up a lot of space. So they'll repel one another the most. They want to be further apart from one another, thereby compressing these bonds closer to one another. So you'll start to see a pattern here. We can have 5 electron groups in total where the arrangement of electron pairs is all considered trigonal bipyramidal. When there are 5 bonds and 0 lone pairs of electrons, we call the molecular geometry still trigonal bipyramidal. So still 5 groups here when 4 of those are bonds and 1 of those groups is a lone pair, like we see here. The molecular geometry or shape that we call that now is a distorted tetrahedron. We're going to put that lone pair to where it can be furthest away from every other group. So it's going to be in the equatorial position, so here. It'll even compress these bonds here in the axial position a little bit further away from that lone pair. That lone pair of electrons doesn't want to be close to anything else. So it's going to push these groups closer to one another. It takes up a lot of space. So under 5 electron groups, 4 bonds, 1 lone pair, we do have the next case where we have 3 bonds and 2 lone pairs. Those 2 lone pairs will again be in the equatorial position. So we still call this trigonal bipyramidal, but the molecular geometry or shape when there are 2 lone pairs and 3 bonds amongst the 5 electron groups. You can kind of see it better in this view. We call this a T-shaped molecular geometry. You can kind of picture here, it looks like a T if you turn your head this way. So turn your head this way, it looks like a T. So T-shaped molecular geometry for 5 electron groups for trigonal bipyramidal. But 3 of those groups are bonds and 2 are lone pairs. Still within 5 electron groups, so still trigonal bipyramidal arrangement of electron groups, we have one more case. So still 5 groups in total. Now 2 of those groups, if they're bonds, and 3 of those groups, if they are lone pairs, is going to look like this. The angle here between these groups in the equatorial position, do you remember what that is? Those are 120 degrees. So in the equatorial position like this, about 120 degrees difference between the lone pairs. Just to show that here, this is slide 10 in chapter 10, part 1. So the groups here in the equatorial positions, those are all separated by a triangle essentially. So 360 divided by 3. There's an equilateral triangle here, so that bond angle is 120 degrees. The bond angle between the axial position and the equatorial position, that is a 90-degree right angle. So to place the lone pairs, which repel each other the most, they take up the most space, we have to put those lone pairs in the equatorial position, so they're the furthest apart. They're all 120 degrees apart. So we put the 3 lone pairs here. Now what we call this molecular geometry, we call this molecular geometry as linear. So you can see why it'd be called that. Kind of looks like a line. Almost like there are just 2 groups, but really 3 of the 5 groups are lone pairs and 2 of the 5 groups are those bonds. So that was it now for 5 electron groups. Then lastly, we're looking at 6 electron groups in total. For 6 electron groups, we call this arrangement of electron pairs as octahedral. When there are 6 bonds and no lone pairs, we still call that molecular geometry as also octahedral. But if we have amongst the 6 electron groups, 5 of them are bonds and 1 of those groups is a lone pair of electrons, that lone pair can go in any one of these positions because these bonds are all the same. But putting a lone pair here sort of compresses the other bonds towards one another. We call this molecular geometry or shape as square pyramidal. You can kind of picture it here. These 4 groups coming up to sort of form a square pyramid. So molecular geometry for 5 bonds and 1 lone pair, we call square pyramidal, still all under the arrangement of electron pairs as octahedral. So 6 electron groups in total is octahedral arrangement of electron pairs. We have one more example we'll look at amongst the 6 electron groups. if amongst those 6 groups we have 4 bonds and 2 lone pairs, we'll put those lone pairs to be as far apart as possible, so on one side going up and on the other side going down, because again, the lone pairs take up a lot of space. So those lone pairs will repel each other. They want to be as far apart as possible. So 6 groups now. This is octahedral arrangement of electron pairs, and the molecular geometry or shape is now called square planar. Can kind of picture this in the plane. We see the square shape. So square planar when we have 4 bonds and 2 lone pairs. This is a nice summary table in your book, so table 10.2. So check that out for a good summary of the different shapes we just looked at. Given that background now and what we did previously in chapter 10, part 1, let's go through a little bit more of a 10.1 example that's in the main slide deck and in your book. So now let's go through A and C together as part of 10.1. What is the very first step always before we can predict the molecular geometry or the arrangement of electron groups? We always first need to draw the Lewis dot structure. That has to come first. So arsenic here, it is in the same group as nitrogen and phosphorus. That means that arsenic has 5 valence electrons, then hydrogen has 1 valence electron times 3. That means we have 8 electrons to work with. We know hydrogen cannot be in the middle, so it has to be on the outer ends of the molecule. So for this molecule, which is also a compound because it's composed of 2 or more unique atoms, or 2 or more unique elements, so arsenic and hydrogen, we're going to put hydrogens around arsenic like this. Just drawing the skeleton, we know hydrogen wants a filled duet, so here already it has a filled duet. How many electrons have we used so far? Well, 2 in each bond, so 1, 2, 3, 4, 5, 6. That means we have 2 electrons remaining, and we're looking at what doesn't have a filled duet or octet. Currently, arsenic only has 6 electrons around it. It needs 2 more for a filled octet. Putting that lone pair there on arsenic, now we've used up all the valence electrons. The 3 hydrogen atoms all have a filled duet, and then arsenic now. So it was 1, 2, 3, 4, 5, 6, now 7, 8. So arsenic now has a happy octet. This is a good Lewis dot structure for this compound. Given this Lewis dot structure, we can see there are 1, 2, 3, 4 total groups around the central atom. So for the arrangement of electron groups, we have 4 groups in total. The electron pair arrangement, therefore, is then tetrahedral. 4 groups in total. We're not yet looking how many of those 4 groups are bonds versus lone pairs. For its molecular geometry or shape now, we do need to differentiate. Here we have 1 lone pair and then 3 bonds from the central atom. So under this category of 4 electron groups and tetrahedral arrangement of electron pairs, we have 3 bonds and 1 lone pair. So now its molecular geometry or shape is trigonal pyramidal. So its shape is trigonal pyramidal. Its arrangement of electron pairs or groups is still considered tetrahedral. So tetrahedral for the arrangement of electron pairs, and for its shape, though specifically, it is trigonal pyramidal. Okay, so let's do another practice now where we differentiate the arrangement of electron pairs versus the actual molecular geometry or shape. Before moving on for this one, I do want to point out that because we do have one lone pair, ordinarily for tetrahedral with all 4 bonds, we know the bond angle is about 109.5 degrees. If we have a lone pair of electrons, however, it's going to compress these bonds just a little bit. So that bond angle is going to be less than 109.5. What would that bond angle be again then? Well, it's about 107.3 when we have 3 bonds and 1 lone pair, so about 107.3. So bond angle less than 109.5, we know it's really about 107.3. So now we've addressed the arrangement of electron groups, as well as the molecular geometry or shape, and now the bond angle as well. Let's try this polyatomic anion. Aluminum is in the same group as boron, so aluminum has 3 valence electrons. Chlorine is a halogen. It has 7 valence electrons, times 4 is 28. So far we have 31 electrons to work with, but we have to notice that we have an anion here. So we have a -1 charge, meaning we need to add on 1 additional electron because of that -1 charge. Chlorine is definitely more electronegative than aluminum, so let's put aluminum in the middle and then draw the skeleton around. So far we've used up 2 electrons per bond, so 1, 2, 3, 4, 5, 6, 7, 8. With all these electrons remaining, we need to start placing those electrons around the more electronegative atoms, which is definitely chlorine in this case. To fill chlorine's octet, we can do 1, 2, 3, 4, 5, 6 around each one. 6 times 4, that means we then have used up those 24 electrons and we have 0 remaining. Did we fill everyone's octet? Well, aluminum, yes. 1, 2, 3, 4, 5, 6, 7, 8. For chlorine, also yes. So 1, 2, 3, 4, 5, 6, 7, 8. This is a good Lewis dot structure for this compound. We've used all the electrons. We've filled every atom's octet. And looking at the total number of groups around the central atom, we definitely have 4 electron groups. That means we're dealing with tetrahedral arrangement of electron pairs. So the arrangement of electron pairs is tetrahedral. And I forgot something very important here, that I need to put brackets around this anion. So for all ions, cations, and anions, I can't forget the brackets and then that charge on the outside. So these brackets around, then that charge, this is a -1 charged compound. If we added up all the formal charges, we'll get a -1 formal charge. To show that, let's do it for aluminum, because I have a feeling aluminum is the atom contributing to this -1 overall charge for this anion. So let's see how this all adds up to -1. Aluminum, looking at its placement in the periodic table, it has 3 valence electrons. There are no lone pairs of electrons, so -0, and I'm getting the formal charge here. Then 1/2 times the number of electrons in bonds around that atom, 1, 2, 3, 4, 5, 6, 7, 8. 3 minus 4 is a -1 formal charge. So from aluminum, this is where the overall -1 charge comes from for the whole compound. It's because aluminum itself has a -1 formal charge on its atom. What about the molecular geometry or the shape? Do we have any lone pairs around the central aluminum? Well, around the central atom, we only have 4 bonds. So the molecular geometry or shape, therefore, is also considered, this is also considered tetrahedral. The bond angles then for tetrahedral where we have all bonds and no lone pairs off the central atom is then also 109.5 degrees. So because no lone pairs are present, the arrangement of the bonding pairs is the same as the electron pair arrangement, or the shape is the same as the electron pair arrangement. The shape then, the molecular geometry, is also therefore tetrahedral, with a bond angle of about 109.5 degrees. I didn't go through all examples in 10.1, so you could look back at 10.1 in the main slide deck for more practice. Let's do another practice problem together here, and let's look at this ion. We're going to predict what is the angle between the carbon-sulfur bond and the carbon-nitrogen bond in this thiocyanate ion, or SCN-. The very first step is always drawing the Lewis dot structure. Sulfur is in group 6. It has 6 valence electrons. Carbon has 4 valence electrons. Nitrogen has 5 valence electrons. This is 15 electrons, but we do importantly need to notice that we have an anion, so we're adding on 1 more electron here. Out of sulfur, carbon, and nitrogen, which one is the least electronegative? Well, on the periodic table, carbon is furthest to the left. Carbon is the least electronegative, therefore carbon goes in the middle. We could also tell from the wording here that we're going to have a carbon-sulfur bond as well as a carbon-nitrogen bond, meaning that carbon has to be in the middle to achieve these 2 bonds. So it doesn't matter what side we put these on. We'll put sulfur and nitrogen just to get us started, and I drew 1 bond between for the skeleton structure. So far then, we've used 1, 2, 3, 4. So we have 12 electrons remaining. We know with those 12 electrons, we need to put them around the more electronegative atoms. So let's start placing these 12, but we can't go against their octet. 1, 2, 3, 4, 5, 6, 7, 8. Sulfur has a happy octet. I have 6 electrons left. I can try to put them around nitrogen, and let's see what's going to happen. So I've used up all the valence electrons, but it's pretty clear that carbon in the middle does not yet have a happy octet. Nitrogen is usually one of our more odd atoms that it likes to form double and triple bonds. So when we're given an option like this, we should start with the lone pair of electrons on nitrogen and try to bring that in to see if we can help carbon's octet. So pulling that lone pair of electrons in results in this structure. Does carbon have a happy octet at this point? 1, 2, 3, 4, 5, 6. Well, not yet, so we should try to bring in yet another lone pair of electrons from nitrogen. So nitrogen, again, is okay with double and triple bonds. So for an option like this, start pulling in lone pairs of electrons from nitrogen. If we pull in this lone pair, a second lone pair, we'll end up with this structure here where we have a triple bond. Then we have 1 lone pair remaining on nitrogen. Does everyone have a happy octet at this point? Sulfur, 1, 2, 3, 4, 5, 6, 7, 8. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. So again, when we have to, we can try to pull in lone pairs of electrons from nitrogen to form double and triple bonds. This is a happy, satisfied Lewis dot structure. We've used up all the valence electrons, and every atom has a happy octet. Don't want to forget this time, so because this is an ion, I definitely need to add in the brackets and the charge on the outside of those brackets. So let's add the brackets in. This is a -1 charge. So this is now my final Lewis dot structure for this compound. So again, as always, we want to draw the Lewis dot structures first for all these geometry style questions. From the complete correct Lewis dot structure, we can tell that we have 2 groups around carbon. One of those groups is the sulfur-carbon single bond or carbon-sulfur single bond. Remember that a triple bond also just counts as 1 group. So the carbon-nitrogen triple bond, that is also just 1 group, making this 2 groups total. The single bond is 1 group, the triple bond is the second group. So just emphasizing this again here, 1 group can be a lone pair, a single bond, or even just a triple bond or a double bond. Those all count as just 1 group apiece. So here in this correct Lewis dot structure, we have 2 groups off of the central atom of carbon. To separate out those 2 electron groups, we need to think about linear arrangement of electron groups. For linear arrangement, or only 2 groups off the central atom, linear is the arrangement of electron groups, and linear is also how we classify its molecular geometry or shape. For 2 groups, it's always linear and linear. So showing that here now from chapter 10, part 1, we can only have just 2 bonds to the central atom. This would be just a single atom on its own. And so this is not possible, of course, when we have 3 different atoms we're working with. For 3 different atoms, for 2 groups around the central atom, we have linear arrangement of electron pairs and linear molecular geometry. For 2 groups, it's always the same. Arrangement of electron pairs is linear, molecular geometry is also linear. We know we'll start to possibly see differences in the arrangement of electron pairs versus the molecular geometry when we start to get into 3 or more electron groups around the central atom. For our practice problem right now, we just have 2 groups around the central atom. So the arrangement of electron groups is linear. The molecular geometry or shape is also linear. We still need to think about the bond angle, and so for either case, when it's linear, this is 180 degrees that separates those 2 electron groups or 2 atoms that are bonded to the central atom. So it does not matter here that 1 group is a single bond and 1 group is a triple bond. This is about 180 degrees, and this is also about 180 degrees. So again, the single, double, or triple bonds in the structures don't matter for bond angles as much. So then what does impact bond angles substantially? It's when we start to bring in lone pairs of electrons to substitute in for bonds. Lone pairs of electrons substantially impact the bond angles. Like we saw for tetrahedral, 4 bonds, 109.5, 3 bonds, and a lone pair, now that bond angle is 107.3. 2 bonds and 2 lone pairs, now that bond angle is 104.5. For our case here, single bond and triple bond, no lone pairs then, this bond angle 180 degrees, and then this bond angle 180 degrees. So the sulfur to carbon bond and the carbon to nitrogen bond, all just 180 degrees for this linear arrangement of electron groups. and linear molecular geometry or shape. So 180 degrees for both bond angles, that's our final answer. We're at the very end of chapter 10 and the very last part of chapter 10, so I'll finish this off with 2 animations I'll include. If you have any questions about anything, let me know. Thank you all for a great semester, and hopefully I will see and talk to you all soon. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Chemists use valence shell electron pair repulsion, or VSEPR theory, to account for the shapes of molecules. The theory is based on the idea that like charges repel each other until repulsions are minimized. The like charges in this case are the groups of valence electrons around a central atom in a molecule or ion. We'll represent them as bars attached to a sphere and show the electrostatic repulsions as yellow arrows of varying width. The simplest case has 2 negative groups around a central atom. At any angle less than 180 degrees, electrostatic repulsions push the bars apart. Repulsions are minimized when the bars attain a linear arrangement. Electron groups can be single bonds, as in gaseous beryllium fluoride, double bonds, as in carbon disulfide, triple bonds, as in hydrogen cyanide, or, as you will see shortly, lone pairs. 3 negative groups attached to a central atom attain minimal repulsions in the trigonal planar arrangement, which has an ideal bond angle of 120 degrees. We observe this angle in molecules with 3 identical groups, such as boron trifluoride and sulfur trioxide. Molecular shape is determined by the positions of atoms, not electron pairs. Therefore, if one of the electron groups is a lone pair, the molecular shape is not trigonal planar, but bent, or V-shaped. Since a lone pair is held by only one nucleus, it is less confined in space and exerts greater repulsions on nearby bonding pairs. As a result, the bond angle is less than 120 degrees, as you can see in this model of ozone. 4 electron groups around a central atom attain minimal repulsions in a tetrahedral arrangement, which has an ideal bond angle of 109.5 degrees. The tetrahedral shape is very common, especially in organic molecules. An example is methane, the simplest hydrocarbon. With one of the 4 electron groups a lone pair, the shape is trigonal pyramidal. Since a lone pair exerts greater repulsions than a bonding pair, the bond angle is less than 109.5 degrees. Ammonia is a common molecule with this shape. Its bond angle is 107.3 degrees. When 2 of the 4 groups are lone pairs, the molecule has a bent or V shape. 2 lone pairs exert greater repulsions than 1, so the bond angle is reduced even further. Water, for example, has a bond angle of only 104.5 degrees. 4 electron pairs fill the valence level of a period 2 atom, but 1 from period 3 or higher can use d orbitals to expand its valence level and bond to more than 4 atoms. 5 electron groups minimize repulsions when they point to the corners of a trigonal bipyramid. Here we find 2 ideal bond angles. Equatorial groups lie 120 degrees apart, and axial groups lie 90 degrees away from equatorial groups. When phosphorus reacts with excess fluorine, the trigonal bipyramidal molecule's phosphorus pentafluoride forms. Once again, when lone pairs are present, different shapes result. but a lone pair in an axial position creates 3 strong 90-degree axial equatorial repulsions, whereas a lone pair in an equatorial position creates only 2 90-degree repulsions. Therefore, to minimize the number of 90-degree repulsions, lone pairs always occupy equatorial positions. As before, lone pair repulsions reduce all other bond angles. With one lone pair, the object has a seesaw shape. Sulfur tetrafluoride is an example. With 2 lone pairs, the object is T-shaped, and the 2 remaining angles are less than the ideal 90 degrees. Bromine trifluoride is a T-shaped molecule. The final shape in the trigonal bipyramidal arrangement occurs when a third equatorial lone pair repels the axial groups to 180 degrees. The object has a linear shape, as in the case of the triiodide ion. The final common arrangement has 6 electron groups attached to the central atom. Repulsions are minimized when the groups point to the corners of an octahedron, and thus lie 90 degrees apart. Sulfur hexafluoride has an octahedral shape. Unlike the trigonal bipyramid, all positions are equivalent in an octahedron. So one lone pair can take any position to give the square pyramidal shape, with all bond angles less than 90 degrees. Iodine pentafluoride has this shape. To minimize repulsions, a second lone pair must lie 180 degrees from the first. The 4 remaining bonding groups are repelled to the ideal 90-degree angle and define the square planar shape. Xenon tetrafluoride, one of the first noble gas compounds to be made, is a square planar molecule.
In determining the geometry of molecules, the valence shell electron pair repulsion model, or VSEPR, assumes that repulsions between electron pairs causes them to remain as far apart as possible. The geometry that the molecule ultimately adopts minimizes the repulsion between electron pairs. Click on one of the buttons to compare the geometries of these molecules. Consider the Lewis structures of ozone, O3, and boron trifluoride, BF3. Counting the number of VSEPR pairs of electrons around the central atom of each molecule, we find 3 VSEPR pairs. As far as electron repulsions are concerned, the VSEPR model treats double and triple bonds like single bonds. A lone pair occupies space around the central atom and is also counted as an electron pair. The electron pair arrangement that minimizes repulsion for 3 pairs of electrons is trigonal planar. The angles between electron pairs are 120 degrees. The molecular geometry is the arrangement of the central atom and the atoms bonded directly to it. In BF3, all 3 electron pairs around boron are bonding pairs. The molecular geometry is trigonal planar with bond angles of 120 degrees. In molecules with no lone pairs around the central atom, like BF3, the electron pair arrangement and molecular geometry will be the same. In ozone, there are 2 bonding pairs of electrons and 1 lone pair. The molecular geometry, that is, the arrangement of the 3 oxygen atoms, is bent or V-shaped. The lone pair versus bonding pair repulsion is greater than the bonding pair versus bonding pair repulsion. The 2 oxygen-oxygen bonds are pushed together slightly due to repulsion with the lone pair, and the bond angle is slightly less than 120 degrees. Consider the Lewis structures of methane, CH4, ammonia, NH3, and water, H2O. Counting the number of VSEPR pairs of electrons around the central atom of each molecule, we find 4 VSEPR pairs. Don't forget to count lone pairs. The electron pair arrangement that minimizes repulsion for 4 pairs of electrons is tetrahedral. The angles between electron pairs are 109.5 degrees. The molecular geometry is the arrangement of the central atom and the atoms bonded directly to it. In CH4, all 4 electron pairs around carbon are bonding pairs. The molecular geometry is tetrahedral with bond angles of 109.5 degrees. In NH3, there are 3 bonding pairs of electrons and 1 lone pair. The molecular geometry, that is, the arrangement of the nitrogen and 3 hydrogen atoms, is a trigonal pyramid. The lone pair versus bonding pair repulsion is greater than the bonding pair versus bonding pair repulsion. The 3 nitrogen-hydrogen bonds are pushed together slightly, and the bond angle is less than 109.5 degrees. In water, there are 2 bonding pairs of electrons and 2 lone pairs. The molecular geometry, that is, the arrangement of the oxygen and 2 hydrogen atoms, is bent or V-shaped. Due to the lone pairs, the oxygen-hydrogen bonds are pushed together slightly, and the bond angle is less than 109.5 degrees. Consider the Lewis structures of phosphorus pentachloride, PCl5, sulfur tetrafluoride, SF4, fluorine trifluoride, ClF3, and xenon difluoride, XeF2. Counting the number of VSEPR pairs of electrons around the central atom of each molecule, we find 5 VSEPR pairs. Don't forget to count lone pairs. The electron pair arrangement that minimizes repulsion for 5 pairs of electrons is trigonal bipyramidal. The angle between electron pairs in the equatorial plane is 120 degrees. The angle between an axial electron pair and an equatorial pair is 90 degrees. The molecular geometry is the arrangement of the central atom and the atoms bonded directly to it. In PCl5, all 5 electron pairs around phosphorus are bonding pairs. The molecular geometry is trigonal bipyramidal with bond angles of 120 degrees and 90 degrees. In SF4, there are 4 bonding pairs of electrons and 1 lone pair. Lone pairs in a trigonal bipyramidal electron pair arrangement will occupy equatorial positions rather than axial positions. In SF4, if the lone pair is equatorial, there are 2 bonding pairs at 120 degrees and 2 more at 90 degrees. On the other hand, if the lone pair were in an axial position, there would be 3 bonding pairs at 90 degrees and 1 pair at 180 degrees. The repulsions are smaller if the lone pair is in the equatorial position. The molecular geometry, that is, the arrangement of the sulfur and 4 fluorine atoms, is a distorted tetrahedron, or seesaw. Due to the lone pair, the sulfur-fluorine bonds are pushed together, and the bond angle in the equatorial plane is less than the typical 120-degree angle. In ClF3, there are 3 bonding pairs of electrons and 2 lone pairs. The lone pairs occupy equatorial positions. The molecular geometry, that is, the arrangement of the chlorine and 3 fluorine atoms, is T-shaped. Due to the lone pairs, the chlorine-fluorine bonds are pushed together, and the fluorine-chlorine-fluorine bond angles are slightly less than 90 degrees. XeF2, there are 2 bonding pairs and 3 lone pairs. The lone pairs occupy the 3 equatorial positions. The molecular geometry, that is, the arrangement of the xenon and the 2 fluorine atoms, is linear. The fluorine-xenon-fluorine bond angle is 180 degrees. Consider the Lewis structures of sulfur hexafluoride, SF6, bromine pentafluoride, BRF5, and xenon tetrafluoride, XeF4. Counting the number of VSEPR pairs of electrons around the central atom of each molecule, we find 6 VSEPR pairs. Don't forget to count lone pairs. Electron pair arrangement that minimizes repulsion for 6 pairs of electrons is octahedral. The angles between electron pairs are 90 degrees. Molecular geometry is the arrangement of the central atom and the atoms bonded directly to it. In SF6, all 6 electron pairs around sulfur are bonding pairs. The molecular geometry is octahedral with bond angles of 90 degrees. In BRF5, there are 5 bonding pairs of electrons and 1 lone pair. All 6 octahedral positions are equivalent, so it does not matter where we place the lone pair. The molecular geometry, that is the arrangement of the bromine and 5 fluorine atoms, is square pyramidal with bond angles of 90 degrees. In XeF4, there are 4 bonding pairs of electrons and 2 lone pairs. The lone pairs are arranged 180 degrees to each other to minimize lone pair repulsion. The molecular geometry, that is the arrangement of the xenon and 4 fluorine atoms, is square planar with bond angles of 90 degrees.